All right, guys. So we need to talk about this laboratory experiment, and it's going to focus on the separatory funnel. A separatory funnel is a very common piece of glassware that's used almost daily in a laboratory environment. And the purpose of a separatory funnel is to do just what the name says, to separate things. And typically what happens is that we put two solutions in the separatory funnel that are not miscible. And again, miscible means mix. So when these two things are immiscible, then that means they will not mix and they should form two different layers on us. And the separatory funnel allows you to put those solutions into a funnel or a piece of glassware. And if you notice the shape of the separatory funnel, it tapers toward the bottom. And the reason that this tapering is happening is because this allows you to easily separate one layer from the other. Now, you probably aren't going to get a 100 complete separation, but you'll get something pretty close. So in this lab experiment, you're going to be using the SEP funnel, and the SEP funnel is basically going to lead you through three different processes. All right, we're going to label this as part A and part B and part C. In part A, what we're doing is that we're introducing you to the separatory funnel and we're giving you two different solvents in order to use and to figure out which one does a better extraction for you. The two solvents that you will be using in this experiment is something called dichloromethane. And dichloromethane also goes by the initials DCM because I get really lazy, and other people do too, and they use the abbreviations instead of the actual whole word. Or it can also go by the word methylene chloride. This is more of a common layman's term for that solvent. So, three different names, but no matter which way you say it, it's going to basically be talking about the same solution. Dichloromethane, DCM, or methylene chloride. And then the other solvent that you'll be picking is something called hexanes, Hexanex. The hex basically means six. And hexanes is a mixture of an assortment, a variety pack in a way, of six carbons that are all hooked up. So they could be in a complete straight chain, or you might see five of them in a row with one hanging off, or you might see four of them in a row and maybe one hanging off here and one hanging off there. So it's just an assortment of different six-membered carbon rings or chains that are present in that solution. Both of these are classified as a carcinogen. All right, so that's something that you kind of want to pay attention to while you work with them in the laboratory. There's no concrete 100% evidence that they cause cancer, but they do kind of warn you not to be smelling the vapors and not to be drinking or bathing in the solutions because this could have a health effect and not a very good one on you. So what will happen is that in the beginning, you will put a solution of iodine into the separatory funnel. And the iodine will be I'm going to call it black brown color. And then you're going to put a portion of methylene chloride inside of the funnel as well. So DCM goes in and you'll get a layer that shows up here on the top. And what will happen is that the brown black iodine color from the solution that we give you, you will gently rock this separatory back and forth, and then you will sit it straight up, and then you will allow it to separate into the layers. And what you'll see is that the brown black color will show up in the methylene chloride or DCM layer. Okay? And then what will happen is that you will take a beaker down here at the bottom, and then you will drain the solution into the beaker. And this you're going to keep. All right? And then what will happen is that you will do this all over again. But this time, instead of DCM, you're going to be using hexanes. So the fresh separatory funnel that's been cleaned and rinsed out very well, your iodine solution goes back inside, a fresh portion of it, and this time instead of DCM, you will use hexanes instead. And the blue, black-brown color will show up here at the top, and then you're going to take another beaker, and you're going to drain it, and you're going to keep it. And then what will happen is that you'll compare the two different colors. Okay? Which one is darker? Because whichever one is darker, that's probably the better extraction solvent out of the two. That means that it's pulled more of the iodine into the solution and separated it from your liquid aqueous solution that was there. All right, so that's the purpose of part A. Pretty simple, pretty quick. There's nothing that you really have to record as far as numbers go. It's all observation based. It's qualitative data here. All right. So for part B, we're going to kind of up the ante a little bit. And instead of iodine, we're going to give you a solution of benzoic acid. Benzoic acid is a very common ingredient in everything from preservatives in food all the way to various forms of skin treatments and creams and lotions, maybe even targeting acne and rosacea. So we see benzoic acid everywhere. It is a common molecule that you use on a daily basis and you don't even know it. Okay, so we're going to have a solution of benzoic acid. And then this procedure is going to be a little bit different. All right, so what I'm going to do is I'm going to erase all of this over here and use the same type of drawing here. The problem is that benzoic acid is colorless. This will be a solution that will look like water to you, and there will be no color associated with it. And that's going to be part of the problem here because you cannot visually see the separation taking place. And some people like that. Some people like to visually see that happen in front of them. But you're not going to be able to do it in part two. All right? So what will happen in this section is that you're going to take a solution of benzoic acid and you're going to put it into a separatory funnel. And I'm going to use BA for benzoic acid. And then you're going to take your extraction solvent. The lab procedure will tell you what to use, and you will add that solvent into the separatory funnel. And in the beginning, I think it says 20 milliliters. So 20 milliliters of solvent goes in, and you rock this back and forth gently, and then you let the separatory funnel stand straight up and down and allow it to separate into two layers. And then what you're hoping is that the benzoic acid that's here will eventually migrate and it will go into that new layer that you just added into the separatory funnel. Now you always have to keep a track on which solution to keep, and the directions will tell you, I believe, in this section, which layer to keep. Do I keep the top layer or do I keep the bottom layer? So pay attention to that because that's what you need to measure. All right, well then just like before, you're going to take a beaker down here at the bottom or an Erlenmeyer flask, I think in this section, and you're going to allow it to drain into the Erlenmeyer flask or beaker, and then you're going to have a solution that you're then going to actually measure. We're not going to play off of what color is it because we can't see the color. So we have to do another chemical test in order to determine how much is actually present. And that's what we're leading up to, right? So then what will happen is that you will set this to a side before you do anything else to it, and you repeat the exact same thing over again. The problem, though, is that you're going to use the same solvent. So we're not comparing solvents in this case, but we're comparing multiple extractions. What do I mean by that? Well, 20 milliliters is what you're going to use in the beginning, and you do it one time, allow it to separate, and that is it. In the second portion of this part, what you will do is you will take 5 milliliters of the solvent, add it to the volumetric flask, or the separatory funnel with a fresh benzoic acid. Make sure that funnel's clean, but you're going to add 5 milliliters of solvent to it. Rock it, allow it to separate, drain it. And then you're going to add another 5 milliliters, rock it, allow it to separate, drain it. And then you're going to do it a third time, and then you're going to do it a fourth time. And if you add all of these up, you're going to get 20 milliliters. So what we're doing is that we're comparing one 20 milliliter addition to your sample versus 4 what we would call multiple extraction steps that still add up to 20 milliliters in the end. So is one shot good enough, or is multiple extractions better? That's what we're after here. All right. So for part B, we're looking for single or multiple. Which is better? In order to determine that, you will then take these two solutions that you've extracted, and the way that we measure them is that we titrate them. Okay, so you've already done a titration before with the burette. This was at the very early parts of the semester. We're going to do the same thing again. We're going to take these samples, put it under a burette. We're going to titrate it to the end point. And the end point for us is going to be pink. So whenever that solution turns pink, that is where I stop and I record the milliliters of titrant that it took. All right. Now the number of milliliters that it took will be put into an equation that's in your laboratory procedure. Very straightforward. The calculation at least is. All right, so finally for part C, what we're now doing is we're using a different compound, and this is salicylic acid. And salicylic acid is very similar to benzoic acid. Salicylic acid is very commonly used in face creams and lotions and acne products as well. So this is another common ingredient or chemical that you expose yourself with to a daily basis. And we're going to do the same thing with salicylic acid. We're going to have a separatory funnel. We're going to put a solution of salicylic acid that's going to be down here in the very bottom. And the salicylic acid is going to be colorless. And then we add an extraction solvent in. We'll do the solvent once. Then we do the solvent multiple times, I think 2 in this case. And we answer the same question. Is the single extraction better, or is the multiple extraction better? Which one gives us a better readout? Well, again, we're going to have to measure this stuff because salicylic acid is clear. So how do we measure it? Well, we're going to add to my solutions that I extract in my beakers, we're going to add a solution of ferric. Now this could be ferric chloride or ferric nitrate, and we're going to add a couple of drops, drip, drip, into each one, drip, drip. I think you actually have a total of 3 in this procedure. Drip, drip. And this will allow it to turn color. I won't ruin what that color is for you. I'll let you kind of find that out on your own when you do it. And then you're going to meet one of the laboratory instructors, myself or Kim, maybe. And you're going to meet us in front of the UV vis instrument. And what will happen is that the UV vis measures color. That's what it's designed to do. So in the very first part, we relied on your eyeballs. Which one is darker, which one is lighter? In this part, well, we're relying on color again, but not with your eyes. The color here is going to be coming from the UV vis spectrometer. So we're going to place the samples in the UV vis, and we're going to get an absorbance value. How much light did it absorb? Well, the darker the color, the more light it will absorb. And then, finally, what you'll do is that we will give you a calibration curve. Okay? and the calibration curve will have a y equals mx plus b associated with it. We will provide this to you. You do not have to generate your own. We'll just basically give you a copy of the graph and say, here's your data. Now go solve. And what will happen is that you'll take your absorbance value from the machine, you will plug it into the y, because absorbance will be plotted on the y-axis, concentration will be plotted on the x-axis, and you will solve for the x variable. And the X will tell you the concentration that you need to report on your data sheet. So this is an actual colored solution that you are proving to us, yes, this solution is colored, but this solution is stronger, this solution is not. So this one did maybe a better job of pulling the sample out of the solution. All right? So that's the laboratory. I know that when you look at the sheet now, it's a bunch of scribble and a bunch of garbage, but hopefully you'll see that this is a very straightforward procedure. It's just testing your technique on a separatory funnel. Can you do it very well? And then can we actually run samples on an instrument to prove to someone else that maybe a single extraction or a multiple extraction works better in the laboratory environment?